button.
Welcome back to Codex. Our speaker today is Radu Balan from the University of Maryland. Professor Balan is an expert in applied and computational harmonic analysis. Today, he'll tell us about factorization of positive semi-definite operators with absolutely summable entries. Take it away, Radu.
John, thank you so much for the introduction, and thank you, the organizers for inviting me here. It's always a pleasure to join the Codex seminar. And thank you all for coming, for attending the meeting. So today I'd like to talk about joint work with, well, a number of people, but particularly today is Fushuai Jiang, Black Jiang, who is joining our meeting as well. And indeed, the title is about factorization of positive semi-definite operators with certain good summability conditions. Thanks to, well, sponsors, at least as they are. And this is a list of works, 2 papers and 1 preprinted, where you can find more information about the results I'm presenting today. Basically, most of the results are included in this last mentioned paper here, factorization of positive semi-definite operators after the summable entries, with a joint work with Black. Okay, so I'm going to start with the motivation. This is a problem that Hans Feichtinger posed about, well, just a little over 20 years ago at the Oberwolfach meeting, interestingly, in 2004. And the problem looks like this. So you are given a positive semi-definite trace class operator T that you write as an integral operator. Tf is integral with this kernel K, right, times the function f. And what you know is that the kernel belongs to this modulation space M1 in 2 variables or 2D variables, x and y. Whatever that means, it's not important to dwell on the modulation spaces too much. I'm going to translate shortly the problem in a more familiar language. But so you have some certain good control on the behavior of the function k of the kernel. And the first version of the question was, if you consider the spectral factorization, this being a trace class, so it's compact operator, you have this sum of rank 1s with hk eigenfunctions properly normalized, so they include the eigenvalue in them. And the question is whether the M1 norms of these eigenfunctions, if you square it, is a square summable. So are the norms square summable? That provides you is a better approximation error, if you want, and it's just simply the operator norm. So if you truncate the sum to t, well, you control the operator norm. That's a property of compact operators, of course. But in fact, you have a better control if you know that the M1 norms is square summable of this of all these eigenfunctions. Well, a modified version of the original question is the spectral factorization goes along the lines that, what about other factorizations? What about if you try t to write the sum of rank 1s, not necessarily the eigenfunctions, some other vectors, gk? Could you get this nice localization property, the M1 norms to be square summable? Okay, so that was about 20 years ago. At the very same meeting in Oberwolfach, Chris Heil and Dave Larson took the problem and translated in a, I guess, easier or more understandable language, the matrix language. That is to say, if you don't want to spend too much time on the modulation spaces, you can read the problem this way. You are given an infinite matrix, okay, so A sub Mn, Mn are non-negative integers, and you know that the entries are summable. So that is a replacement for that M1 condition of the kernel. This sum, so L1 norm of the entries, I call it the 1 norm of A, or as you see, this wedge symbol, which is going to play a certain role, is a projective norm of the operator A. Just from this condition, you already get that the operator A is compact. The trace class compact operator effect is more than that. We assume that A as an operator acting on little L2, okay, so which is a Hilbert space, is self-adjoint and positive semi-definite. Okay, so that's the condition equal to A star greater than or equal to 0. Now you fix a basis, and for which you have this matrix representation, if you want, of your operator. So the, I mean, you have the canonical basis for your space. On the other hand, the operator A, of course, admits an orthogonal set of eigenvectors that you can normalize to carry the eigenvalues. And that allows you the spectral decomposition of A, right? The sum of EK, EK star. It turns out that each EK is in L1, so it's not only in L2, but in fact it's in L1 because of this strong summability condition of A. And the two problems, the two questions I posed earlier are equivalent to the following. The first one is to say, if we take these eigenvectors, are their L1 norm square summable? And and the answer actually ends up to be negative. We showed that in our first publication. But the second one asks the question, is it possible to find the factorization of the matrix A as the sum of rank ones in such a way that the L1 norms of Fk are square summable? Okay, so Fk in the second factorization do not have to be, and most likely are not going to be the eigenvectors properly normalized, but could be some other functions. Right, and if you look at this problem from this perspective, it's natural to use and think the frame theory as being the appropriate and the best framework, right, to play with this. All right, so one interesting consequence of this, so assuming for a moment that the second question has a positive answer, you can actually show that there exists a universal constant, I call it that K sub U, in such a way that any square positive semi-definite matrix, right, let's call it A, so this is finite now matrix, it's not an infinite matrix. You can find a decomposition, so you can write it as the sum of Fk, Fk star, Fk vectors, in such a way that the L1 norms of Fk, the square of these L1 norms, the sum is upper bounded by the one norm of the matrix A up to this constant K. Right, so if the second question, if Q2 has a positive answer, then there must exist a universal constant that satisfies this inequality. So this actually started a line of research, at least for me and for collaborators we had for this couple of years. And I'm going to tell you, the story for this problem, that is to say what this problem means, this last inequality, or different type of quantities, right, associated in this inequality. And then we're gonna, so one of the breakthrough we had a year ago was to convert this inequality from decomposition factorization of the matrix A into some quadratic bounds of just symmetric matrices. And we got stuck with that one for a couple of months. But at an other Obo-Bofak meeting, that was exactly 20 years later, last year, a trio of musketeers, and one of them being Dustin, who is actually just here and laughing out loud, I guess. He's muted, so he's just laughing out. Answered the question, right? Exactly this inequality of whether such a constant exists or not. And as it turns out, the answer is negative, which, looking at the proposition, you go backwards, right? Since the answer is negative, it follows that the answer to Q2 is also negative. So we'll get to that one toward the end. All right, so let me continue then. As a warm-up exercise, right? So suppose that you're given a matrix. This is square, but not necessarily symmetric, right? In fact, it doesn't even have to be square. It could be just a rectangular matrix, real or complex numbers. And you're looking over all possible decompositions of A as sum of rank ones, again, not symmetric, xk, yk transpose, right? I don't even specify how many, but I'm looking at this objective function. What you want to do is to minimize the sum of L1 norm, the product L1 norm, right? The xk and yk that contributes when you expand the matrix A, right? And let's try to figure out what's the optimum value, right, for this infimum, what the smallest that can get. Well, if you think a little bit, for instance, if the matrix was already diagonal, you may say that all these xk, yk are like 1, 0, 0, and so on, and you just have to scale by the diagonal elements. So it ends up to be, at least, it has to contain the sum of the absolute value, perhaps, of the diagonal elements, and in fact, more than that, sum of all absolute values. In fact, it turns out that that is exactly the optimal value. And here is here is an example how this works. So you can take your matrix and take each column, right? You separate column by column, and you multiply the first column with a row vector 1, 0, 0, 0, and you get a matrix where you obtain the first column, everything else is 0, and you do the same with all the other matrices. You get matrices that are sparse and containing one column at a time, and you can recover the matrix A by adding all these objects. Well, it turns out that the optimal value, gamma A, whatever it is, it has to be at most, the sum that you achieve here, which is the L1 norm of A, what I mentioned earlier. But in fact, it turns out that this is not only an upper bound, this is in fact the bound. And here is kind of a short line why that is the case. Basically, you show that for rank 1's xk, yk transpose, no matter what type of decomposition you try, the gamma associated to one such object would have to be equal to the product of L1 norms of xk and yk. Once that is established, well, you go backwards and say, find the one norm of A, which would be the one norm of the sum of rank 1's. It's upper bounded by the sum of one norms of these guys, which is a product of one norms. And that was, if those are the optimal decomposition, that would recover gamma A. Right. Well, there is a technicality within infimum. In fact, it turns out that, obviously you can play with epsilon type arguments, but it turns out that the infimum is in fact the minimum. I mean, this is clearly showing that you don't have to use more than n vectors. So, okay, so this was the easy part, right? Like a norm up exercise, the infimum, if you allow xk and yk to different vectors, you get exactly this lower bound for gamma. In fact, it turns out that this lower bound has a very nice interpretation in nuclear operator theory. Grothendieck introduced some 70 years ago. And this is referred to sometimes as a projective norm, right? And so, I mean, for a while, at least the beginning, Grothendieck and his constant kind of played a role and in this game. Okay, now if you have, however, if your matrix is symmetric, right, you have more structure to it. Let's constrain the problem so that xk and yk cannot just be independent arbitrary vectors, but I want xk and yk to either be xk or negative xk in the real case. In other words, I want xk transpose, and I put a sign factor epsilon k in front, right? And we set up the same problem. We minimize. We want to infimum sum of L1 norm square of these vectors xk, the building blocks for the matrix A, but you allow to add and subtract rank 1's. Okay, let's call that one gamma 0. Well, gamma 0, interestingly enough, first of all, it ends up to be a norm. A is symmetric, right? It doesn't have to be positive semi-definite, and you can compute gamma 0 on a vector space, and on that vector space, gamma 0 ends up to be a norm. Now, it has to be greater than or equal to the one norm here of the matrix A, simply because you constrain the problem. Right, so the feasibility space gets smaller. So gamma 0 can only be, I mean, at best it's bounded below by the one norm, or it would have to be larger than that. It's not hard to show this is a norm, so you just play a little bit and you see that it's a norm. You can in fact do more than that. You can show that gamma 0 on one hand is bounded below by one norm, as I said, but in fact it's bounded below by 2 times one norm. How you do that? Well, you just leverage the symmetric outer product, xy transpose plus yx transpose, half of it. You can write it as the difference of this symmetric rank 1's. And then once you know an optimal decomposition of A in the gamma A, the one that I showed earlier, you try to do it this way, but you also have to balance the norms of x and y to make it work. And you eventually end up with a factor 2 here. As a side remark, it's not the focus of the talk, but it's easy to show that 2 is an optimal constant if you say A is a symmetric matrix. You can always find a symmetric matrix which achieves here the upper bound 2. Something like 0, 1, 1, 0, I believe. So something that has plus and minus eigenvalues, like that one, which is going to achieve this upper bound 2. open problem, at least for me, I mean, there are two open problems for him. One is in this context. One is I don't know exactly the optimal upper bound here too if A is positive semi-definite. So on the positive semi-definites, I don't know whether it's smaller than 2 or 2, it can still be achieved. Who knows? Maybe it might still be achieved, but I don't know. And the second problem is computational. Actually, I don't know how exactly to compute gamma naught of a matrix A. I mean, I know it's in between, but and you know, some cases, okay, you can get the lower bound or the upper bounds, and I mean the lower bound, in which case you know that is the optimal. But in general, actually, I don't know exactly how to compute gamma naught. But well, anyway, so this is kind of a side comment at this point. All right, so gamma naught, you optimize this L1 norm square, the sum of them subject to the constraint. You are allowed to add and subtract rank 1, symmetric rank 1s. Well, moving on with another constraint, let's say that you only allowed to add rank 1s, right? You're never allowed to subtract, you only go up. So you put an x1 transpose, okay, so here's the typo, it's supposed to be xk. And your objective function is the same. You want to minimize the square of L1 norms of these building blocks. And I'm going to call this one gamma plus. Obviously, this works only for positive semi-definite operators, right? It's not going to work for if you have something negative, a negative eigenvalue. The focus is to figure out what is this gamma plus and how does it sit with respect to, well, the norm, first and foremost. And as you'll see, this is very much related to the original problem that I had. This is, in fact, yeah, that's a quantity that was showing up earlier on. It's obvious this chain of inequalities simply because gamma plus as an optimization problem is more constrained than gamma 0. So this quantity can only increase. And okay, so let me state here the matrix problem is to say, what about bounding above gamma plus by one norm of A? Well, the best possible constant I'm going to call Cn, right? So Cn is that positive number such that gamma plus of A is always bounded above by Cn times one norm of A, right? Cn is going to be greater than or equal to 1. And what we want, ideally, we'd want to find exactly the Cn, the value of Cn. How does C depends on the size of the matrix M, which is the supremum of this ratio, gamma plus by one norm of A, right? Over positive semi-definites. Okay, and this is gonna, I mean, I'm gonna make comments about this one over the next slides, but this may actually take about 10 minutes or so to get some feeling about how gamma plus and the one norm of A are related to one another. All right, so that's the main focus for the next couple of minutes. I don't know if are any questions up to this point. I'm looking on my other screen. That's good. All right, so okay, let's discuss properties of this quantity gamma plus. First of all, I claim that gamma plus is in fact, while it's defined as a infimum, is in fact a minimum is achieved. And it turns out that you don't need to use more than, for instance, n squared rank 1s. In the complex case is n squared, the maximum number in the real case would be like nn plus 1 over 2. The number is related to the dimension, the real dimension of the space of symmetric matrices. So in the real case would be this nn plus 1 over 2, in the complex case is n squared, which in turn is related to the Minkowski-Kara-Teodori theorem, right, about convex sets and the number of extremum points, right, that are needed to span to generate any point inside the convex set. That's where that dimension comes from. So that's good news. So you don't need to search or consider more than, for instance, square of the dimension, right? How many such rank 1s you need. The bad news is that we don't know what those vectors are, right? And that's kind of a part of the problem. Now, upper bounds. Well, it's easy to upper bound, for instance, gamma plus by n times the trace. It's kind of switching from L1 to L2. If you know that A is decomposed as a sum of rank 1s, you want to compute the L1 norms of xk and then square. use a Cauchy-Schwarz and you switch, from one place to the other, and basically how you get the n trace A, which is upper bounded by n times the sum of all absolute values of entries, right? So an upper bound for Cn is automatically you get n little n, right? You can also bound gamma plus, well, n trace, and another way the trace is bounded by n times the operator norm, right? The largest singular value. Keep in mind A is positive semi-definite, right? So you get this upper bound as well. All right, these are kind of the easy side. On the lower side was even easier. I said that A1, the one norm, is a lower bound. Okay, other properties. So gamma plus satisfies convexity relationship. For instance, if you take two positive semi-definites and you look at the gamma plus of the sum, well, is upper bounded by the sum simply because, well, you take the optimal decomposition of, for instance, either one, A and B. I mean, you take the optimal decomposition of A and B, I should say, respectively. That provides you with A decomposition for A plus B, so the gamma plus can only be less than or equal to whatever that feasible decomposition of vectors provides you, and therefore, in turn, that give you gamma plus of A plus gamma plus of B. So in general, when you have an optimization problem, your objective function is the infimum of something, you kind of get the convexity, subadditivity, I should say. And the second part is homogeneity. And again, this works out fine. You take the norm square, A involves quadratic relations as well. So you end up with this homogeneity. So if you look at these two properties, the convexity, so subadditivity and the homogeneity, you may say gamma plus is a norm, right? Looks like a norm, but it's not a norm simply because you apply only on this cone of positive semi-definite matrix. You cannot apply gamma plus on the whole space. The feasible set is empty in that case. Okay, here are just examples of a numerical experiment. What the curves are, basically there are two algorithms. One is using the spectral decomposition, the other one using the LDL decomposition, which is kind of an LU, but for symmetric matrices. Positive semi-definite, for instance, you obtain the U part is exactly transpose of L. Well, you can take the diagonal elements then and put them in the D matrix, and that's how you get the LDL factorization. So these are factorization that result in n rank ones, not n square, right? And we're just looking at what happened to the L1 norm square, for either of the two algorithms divided by L1 norm of the matrix, and look at the maximum. Horizontally is the size of the matrix, so the thousands. Here's 2,000, here's 10,000, right? And running the experiment multiple times, 30 times, you look at what happens with the ratio, right? The upper bound n would correspond to a straight line, which would go relatively quickly, right? But luckily, I mean, as you see, it's a curve that bends, so it doesn't go as bad as n. In fact, it turns out that the eigen decomposition, you can actually come up with examples that achieve this upper bound n. So the eigen decomposition is technically bad, but those are not very frequent examples. That's why in the eigen decomposition, which I think is the curve above, right, the larger number of the two, well, it's a larger, but it doesn't go to n. I mean, it's not that bad in general. You have to construct those examples, not randomly. You're not going to generate very easily. All right. Okay. Good. So these are kind of the easy type bounds. Now, more properties, and here is a slide where I compressed quite a number of properties, and I'm trying to decompress what I'm saying here. So the first part says, look, these are cases when I know how to compute gamma plus. So gamma plus ends up to be exactly the one norm of A in these three cases. One is that when A is already of rank 1, XX star, which in fact gives you the optimal decomposition just as well. The second one is that when A is diagonally dominant matrix, so the diagonal element AII is greater than or equal to sum of absolute value of diagonals on that row or column, right? And the third one is when A admits what is known as a non-negative matrix factorization. I think that is also in some other circles termed as completely positive map, if I remember correctly. Well, so that means that A can be written as a BB transpose, right? B doesn't have to be square. I mean, J is not square, but the entries in B are non-negative. And again, it turns out that, in fact, the columns of B would provide you with the optimal decomposition. And in all these cases, gamma plus is equal to the one norm of A. In some sense, great, but the bad news, and that's kind of an interesting open question here, that the only cases when I know how to compute gamma plus is when it ends up to be the one norm of A. In all other cases, I do not know how to compute it. So we know that it's not always gamma plus equal to one norm, but I don't know, numerically how to do that for matrices, let's say more than 5 by 5. I mean, including 5 by 5. So that's a downer, I guess. Now, at the in terms of properties, so there are okay. So the next one was about continuity, and it took a while actually about the continuity. I don't know, well, why, but we can show, and ultimately I have in slides later on in case somebody is interested in how to do that. Gamma plus ends up to be continuous on the entire closed cone of positive semi-definite matrices. Now, if you have a lower bound on the matrices, let's say 2A and B bounded delta times I, you can in fact derive some Lipschitz property. So you see the gamma plus A minus gamma plus B is upper bounded by the operator norm of the difference. You can use any norm here, of course. And then the Lipschitz constant, or at least an estimate of the Lipschitz constants, has dependency on the size n as well as delta, the lower bound. And obviously, as delta approaches 0, this part blows up. I mean, I'm not saying that it's not Lipschitz. I'm just saying that, or I don't know if it's a Lipschitz or not, but I'm saying that this method, this approach would give you this 1 over delta dependency here. Now, the third property is going to be very interesting, and this is going to take us eventually towards these quadratic bounds and kind of the second part of the. Okay, so here is in terms of the framework. So I denote S sub 1 the unit sphere, right? But with respect to L1 norm. So this is like the diamond. Looks like that's the shape of a diamond. And the B of S1 is a set of Borel measures over S1. So these are, well, measures of positive valued or non-negative valued number function over the set of, over the collection of measurable sets, Borel measurable sets of the sphere. Now, what do we want? We want to solve the following. So I'm going to formulate a seemingly more general problem. And that is to say, among all possible measures that satisfy a certain constraint, I want to find the measure that minimizes the total measure of the sphere. Now, the measures are Borel over the sphere. The constraint is that if you integrate this rank 1 xx star with respect to the measure, you have to recover exactly the matrix A. So that positive semi-definite matrix A given to you, the n by n. If you integrate, so what it means that you integrate, for instance, xi times xj bar, if we're dealing with complex sphere, or xi xj in the real case with a measure over the sphere, you end up exactly with a sub ij, that particular number, right? So it's kind of, I mean, definitely it's the second moment condition, right, for this measure. The measure in general is not going to be unique, the solution, but here's the thing. One of the minimizers, so in the class of minimizers, you can show that one of the minimizers it's a pure point measure, and in fact it's a sum of deltas Diracs at some vectors gk on the unit sphere with some weights lambda k in front. The gk, the vectors where the measure is supported, and the lambda k, the scalars, are precisely those that would produce, on one hand, a factorization of the matrix A, a decomposition into sum of rank ones, but in fact would be the optimal, it will provide you an optimal factorization with respect to the gamma plus objective function. The gamma plus ends up to be exactly the sum of lambda k. Right, so if you think a bit, if you just look over measures, atomic measures, right, that have some, decompositions, finite sum of deltas, and you substitute here, the total measure will be exactly the sum of lambdas, the weights, and the constraint would be translated precisely in the decomposition of your matrix A as a sum of rank ones, right? That would be exactly. So it's easy to show that this is a feasible solution, and therefore the infimum, whatever it is going to be upper bounded by gamma plus. It takes a little bit of time to show the other inequality as well, meaning that gamma plus is upper bounded by this infimum, if you want, plus an epsilon. And yeah, and again, I have in the slides, and if you look into the preprint, we have explicitly proved the statement there. That is one point, that is one place where one has to use the fact that S1 is some sort of a local convexity problem. Specifically, it has to be the boundary of a convex set, right? Which obviously the sphere is, right? If you think about extending to other cases like LP norm, yeah, that would work when LP for P between 1 and infinity. But if you try for P less than 1, it's not going to work. This type of inequality is not going to, equality is not going to work here. You might end up with a constant, but not an exact equality for P less than 1. So convexity is some sort of a strange convexity. Actually, it ends up to be necessary here. Okay, so far what we've done is that gamma plus, which is a hard problem, we translate, if you want, we replaced by even harder problem, right? Which is to optimize over all possible Borel measures, the one that satisfies this feasibility condition. So you integrate rank ones to, and you recover the matrix A, and you want to find the one that has the smallest total mass, right, of the sphere, the total variation. It doesn't seem like we done much progress. In fact, from a hard problem, we got even a harder one. Well, in the next slides, I'm going to translate this problem into a dual formulation, what I call the quadratic bounds, and that will take us into a, kind of a different version of the problem, and it's a, a new exciting one, I'd say. Any questions so far, though? Before we move on. Just again looking at the reaction. Good. Now, so again, in my additional slides, I can show explicitly that in fact this is a linear program. So from that perspective, it's great, except that it's a linear program of an infinite dimensional space because it's over the space of Borel measures. So that's kind of the downside, but it's a linear program. Being a linear program, well, you would expect for linear programs that the strong duality would hold, and that is indeed the case. And this is my comment above here, that is a linear program, which is convex, great, but it's an infinite dimensional space, which is not so great, but enjoys strong duality. And here is how the strong duality works. So gamma plus, I just said earlier, and it's provable that is a minimum of this total variation of a measure mu, that satisfy this feasibility condition, the minimum. Its dual formulation is given here down below. You maximize the trace of TA, so A is given to you, it's positive semi-definite, is fixed, right? You maximize over T. T are just symmetric matrices, no positivity or no sign condition. However, T has to satisfy this bound condition. So what it says is that if you look at the quadratic form TXX, right, TXX, not absolute value of TXX, TXX has to be bounded above by 1 for all unit norm vectors with respect to L1 norm. So all vectors in the diamond, right, the TXX should not exceed 1. And you maximize the trace of TA over all such T matrices. The maximum you get actually matches the minimum from this side, right? And The first one, the gamma plus, and this linear program formulation, I call it the primal. The maximization of the trace would be the dual in this case, right, for this one. And excuse me, let me just give you a quick reason why that is the case. So let's assume for the moment that you know the support of your measure, right? X1 to Xm vectors are known. Let's assume that. And you construct the Lagrange function. So in that case, so I saying that the support is like that, meaning that the mu is of the form summation of tk delta, right, at x minus xk. That's a measure. And therefore the constraint is a minus the sum of tkxk star, right? This must be 0, and I introduce a Lagrange multiplier, a matrix T, trace of T times. This is a Lagrange multiplier term. And then the tk must be non-negative, and this is what the nu k are the Lagrange multipliers for the tk's. And your objective function is the sum of tk. This is a total measure, right? The tk's. And the Lagrange function, what you do, you take the infimum over t. These are your variables, right? That cap t and nu1 to nu_m are the Lagrange multipliers, or the multipliers. And that defines the dual function, the infimum of L over the t here bold is a vector, nu should be a vector. For some reason, LaTeX didn't turn into a vector, didn't turn into a bold. And what you get, in general, you get negative infinity unless something, kind of magically happens. And the magical means you take the derivative with respect to all this tk and you have to have 0. And you take the partial derivative with respect to tk, for instance, is 1 minus the tk shows up here, the trace of t xk star, which gives you the quadratic form, and negative nu k is from here. This must be 0. So if somehow in your search space for multipliers t and nu k, you achieve this 0, then you don't reach negative infinity, you only end up with trace of ta, which is here. Right, and remember, for the duality, well, your primal was minimum. Now you maximize the dual function g over the Lagrange multipliers, which obviously you try to avoid negative infinity. You want to be on the finite side, trace of ta. So you maximize trace of ta, but then you have these constraints on t and then Lagrange multipliers and nu k. Nu k has to be non-negative, and you have to have equality 0 equal to 0 here, which means that the quadratic form txk must be less than or equal to 1, right? So you have this nu k like a slack variable, right? Some space to nu k will pick up the difference. That's where the upper bound for the quadratic form comes. Txx less than or equal to 1 comes exactly from here, right? And this assuming you know the support. If you don't know, then you have to ensure that such equalities will hold true basically for every unit norm vector x, and that's where the second part is. Now comes technicalities, of course. You deal with measures, not finite vector matrices or finitely many vectors, and that's what's good for a preprint, right? To write results and results. Okay, so this try to explains how you get from the primal to the dual. Now I'm pointing out this quantity, which is this quadratic bound txx, on the unit diamond. Let's call it rho 1. And the dual problem, which was to maximize the trace, you can reformulate as maximizing the trace, the condition of t is that rho 1 of t must be less than or equal to 1. This is just replacement for the constraint. Now here's the thing, Cn, the constant Cn, right, from this upper bound, maximum gamma plus of a subject to 1 norm less than or equal to a, you maximize, so the first maximum here is exactly the max we had before, but the gamma plus I'm going to replace through the dual form, max of the trace Ta, subject to t equal to t star, so self-adjoint with rho 1 less than or equal to 1. I'm switching the order of the two maxima, right, because they're maxima. And if you do so, right, max over a first, max over t second, meaning that inside actually the max over t takes place first. Well, so whatever does not depend on t, like 1 norm of a, you can take it outside the maximum. You're looking at the maximum of this ratio, trace ta over rho 1 of t, right? Okay, so I'm gonna get back, sorry, about this one in just a minute. Let me just quickly say something about this rho 1. This is what I call the quadratic bound. that's what we call quadratic bounds. And they are interesting in itself. I mean, they are similar to the numerical radius of a matrix. If you want the singular value, you actually get the largest eigenvalue if instead of L1 norm of X, if you had L2 norm of X, right? That would, you get exactly the largest eigenvalue. But here is L1. The other thing to consider is a max of this TXX, not the absolute value, right? The absolute value would have been closer to numerical radius. But actually, if you remember about what I called gamma 0 earlier, right? That when you're allowed to add and subtract symmetric rank ones, actually the appropriate quadratic bound for the gamma 0 ends up to be the max of the absolute value. So that's interesting to, you can go through these derivations here. In that case, you allow positive and negatives, and well, anyway, that's a separate thing. Okay, some comments about Ron, but I'm kind of running out of time here, and I want to get to punchline. Let's take a matrix T that is not negative semi-definite, so at least one eigenvalue has to be strictly positive, the largest one. And in that case, if you look at the ρ1 of T, which is the max of this quadratic form, well, I said over a unit diamond, in fact, it has to achieve its maximum on the boundary, so on the surface, on the unit sphere. You can write this maximum, right? You can rewrite as a maximum of trace of T times A, where A stands for the XX transpose, or XX star, right? So kind of you linearize the quadratic into a form, but with a matrix A instead of the vector X, right? What are the constraint on A? Well, it has to be positive semi-definite, the XX star. Rank must be 1 to account for the XX star, and the 1 norm of A is 1, the sum of all entries, because that's the L1 norm square of the X, in fact, ends up, right? So the ρ1 of T, this quadratic bound, you can write it as a max of this trace subject to these constraints, right? And again, the equal to 1 norm or less than or equal to 1 would not make a difference because the lambda max is strictly positive and it's going to achieve on the boundary. I'm just wanting to write out, to point out that ρ1 is, well, obviously not a convex optimization, would not have been either equal to 1 or less than or equal to 1 because TXX is not convex unless T is positive definite or semi-definite, but in general, that's not the case. But you can write it in a matrix language, trace of TA subject to these conditions. And the fact that makes it not convex is the rank condition, right? You know that. Well, I'm saying that because a natural convex relaxation of the bound is to ignore the rank condition, right? That's what we do in low rank matrix completion and all the other problems. So remove the rank condition and you maximize the trace subject to A positive semi-definite and norm of A less than or equal to 1, right? And this is a semi-definite program, it's an SDP. Since we relaxed the problem, ρ1 is upper bounded by pi plus. So ρ1, it's a hard problem, at least I think it's a hard problem. Pi plus, technically it's an easier problem, it's a convex, it's a semi-definite program, right? And the question may become, okay, how much of a price do we pay, replacing ρ1 hard problem by an easier, by the convex problem, pi plus? Well, let me skip this trace for a second and to say that, in fact, pi plus, as it stands with respect to ρ1, the quadratic bound, it's exactly, in the worst case scenario, the ratio here, it's exactly the ratio given by, how gamma plus of A is compared to 1 norm of A. And that was a constant Cn, we said earlier. So the Cn, which was the maximum of these two quantities, gamma plus that I like to compute, but I don't know how, divided by 1 norm of A, which is easy to compute. In fact, that ratio, the maximum, is exactly the same as a maximum between pi plus of T, which is an easy quantity or an easier quantity to compute, it's a solution of a semi-definite program, to ρ1 of T, the quadratic bound, which I like to know, but I don't exactly know how to compute it. So we have this equality between the two. Now, the good news, in some sense, is that the second problem may be more tractable in some sense, and that was, in fact, what happens next. So having an answer on this side, pi plus versus ρ1, gives us an insight about what happened to this gamma plus with respect to one norm. Okay, and well, here is just a simple derivation why you have the equality here. It's kind of switching the two maxima. I mentioned at some point that max over A, max over T, then max over T, max over A. You take the 1 over, in this case, rho 1 of T out, and what you are left with on the side is precisely the convex relaxation, the pi plus. That's, you know, how the two quantities are related to one another. So I'll be running out of time shortly. The previous slide was just saying that this convex semi-definite program has also enjoyed a strong duality. There is a dual formulation, you know, if you'd like to do it this way, but, you know, let me skip it just in interest of time. And okay, so this is relationship between the two. And now, next comes our musketeers, right? Dustin here, as well as Afonso and Stefan Steinerberger. So last year, when I presented you know, the results up to this point at the WOFAC meeting, exactly 20 years later, right? And you know, I didn't know how it's gonna end up or turn out. And you know, Afonso and Dustin and Stefan had this brilliant idea to look for candidates for the pi plus and the relationship to rho 1. So candidates for the T matrix, this symmetric, not necessarily positive or negative definite matrix, in a special class that includes basically binary matrices. So matrices with entries in plus minus 1 Bernoulli distributed, and you can add identity to it accordingly to control certain spectral properties. And brilliantly, I would say, they show that in fact, the worst case scenario, meaning that the maximum of the ratio cannot be independent of n. In fact, they found a lower bound that grows up to a constant with the square root of n. So definitely it's not independent of n, but we'll have to grow at least like square root of n. Right, and yeah, so that was a great result, and you know, one consequence, a corollary of the result was, you know, the fact that you can construct now a counterexample to the original problem. You can always find a symmetric, right, positive semi-definite matrix, infinite matrix, with absolutely summable entries, so that any factorization in sum of rank ones will have this L1 norm squared infinity, so it cannot be finite. Or if you translate in the modulation space language, if the kernel is an M1 and defines a positive semi-definite operator, so that's a symmetry of the operator, and the positivity or non-negativity is reflected in this inequality, excuse me, then no matter how you try to expand in sum of rank ones, these are the GNs here, you guarantee that the M1 norms of GN are not square-summable. It's not square-summable. So that would be kind of the no-go type result for here. Now, nevertheless, let me just quickly point out to some results, positive results for the infinite dimensional problem. And that's where I'm going to end the talk as well. So at this point, we have two classes, gamma and gamma plus. Gamma would be just the one that basically are positive semi-definite, infinite matrices with absolutely summable entries, right? So this is the gamma. That's the placement for the M1 space. Gamma plus, well, in addition to have absolutely summable entries, they admit a decomposition in sum of rank ones, where the x case, the generators, the one norm of the x case is square summable. Right? Our problem so far was whether any operator in gamma is in gamma plus as well, right? Gamma, let's call it gamma, little gamma plus of A, the infimum of this, so the optimal decomposition with respect to this one norm square objective function, right? So what the corollary of Afonso with Dustin and Stefan result is the fact that gamma plus, well, is inside but is different. I mean, it's strictly smaller than capital gamma, right? There are objects in gamma but not in gamma plus. That's what we said earlier in the theory. Nevertheless, so what can we still say about gamma plus versus gamma? Well, here are two results. One is, we call it density result, and says the following. Let's take A in gamma. Okay, so you may not be in gamma plus, or maybe it is, but no matter how small an epsilon you give me, I can always find two operators B and C, which are in gamma plus, so they admit decompositions summable in that respect, stronger sense. A, you can write it as a difference B minus C. And gamma plus of C, the part that you adjust, is arbitrarily small, smaller than epsilon. Right, so within epsilon, from that perspective, you can replace A by an operator B, right, which is in gamma plus, which is in the class gamma plus. So it does say the gamma plus is dense in gamma with respect to this one norm topology, but it's a little bit more than that if you read through the lines. In fact, the proof is in such a way that tells you what type of truncations you can do from A to make it work. That's kind of the thing. Okay, that's one side, the density, and the second result, interestingly enough, is the following. So choose your favorite univariate polynomial's non-negative coefficients, and it turns out that if you take an A in this gamma plus class, when you apply P on A, you stay in the gamma plus class. So the gamma plus as a class is invariant to the action of polynomials with non-negative coefficients. Right, I call it algebraic cone here. I mean, one may ask, and I don't know actually yet the answer, there's a winner lemma, right, which says, I mean, if you think about the winner lemma as a function 1 over x, it is positive, right? One may ask, what about other functions than polynomials, right, with non-negative coefficients? Could that leave the gamma plus invariant? And the answer is I don't know yet, but I would not be surprised if that may be the case. Now, keep in mind, gamma plus, though, unlike the, I guess in the winner lemma case, is not a vector space, right? So, and it's not closed either with respect to certain norms or any norm, as far as I know. So, but the fact that it lacks the linearity structure like a vector space, that might create some problems. That's where the non-negative coefficients are important, right? In translating differences. So I would be happy to stop here, and thank you for listening, and I'm open for questions. My time is up, I guess.
Yeah, thanks, Radu. I'm going to encourage everybody to hit that reaction button